Hey folks, I've got one more example for you of angular momentum conservation, and then I've got a quick conceptual question for you guys, which will lead you into, I do have one more example video that this specific conceptual question is going to lead you into. But first, let's do our example. Okay, so right now, all I have on the page is a circle, right? Okay, well, what that circle is representing is a merry-go-round, and we are looking at a top view of the merry-go-round. By the way, they don't make these much anymore, or at least you can't find them here in northern or suburban Chicago anymore. Long story behind that, but when I grew up, we had merry-go-rounds all the time. So let's say it's a top view of the merry-go-round. And let's say you are standing at the very outside and you're holding on to something so you don't fall off. And let's say I give you the following information, okay? Right now, the merry-go-round is spinning, let's just say counterclockwise with some omega naught, okay? The mass of the merry-go-round, let's say it's 200 kilograms. They're usually pretty heavy. Let's say your mass, I'm going to call that little m, or actually it's me. Let's say it's 80 kilograms because, I'm on the merry-go-round going for a ride. And let's say the initial omega, so omega naught, is 1/4 of a rev per second. So it's taking 4 seconds to do one revolution, which equates to, if you times that by 2 pi radians in one rev, you get pi over 2 radians per second. Okay, so that's your starting angular velocity. So here's what I want to figure out for this. You're going to start at the outside and you're going to walk until you're at the dead center. Okay, so what I want to find is when you're at the dead center, what is your omega final? Okay, how fast is the merry-go-round moving then? Now, by the way, if you've ever done this, you know that the merry-go-round speeds up. So the question is, how much does it speed up? And then also, how much work did it take for you to do that? Because you have to push over a distance, okay? So we're going to calculate that, and there's a real easy way to calculate that. So let's first start with the angular velocity. Well, as I travel from the outside to the inside, there's all kinds of forces between you and the merry-go-round. But if I look at external to the person merry-go-round system, there's no unbalanced external forces. So therefore, there's no unbalanced external torques. Therefore, the total momentum before you crawl toward the center is going to equal the total angular momentum after you crawl into the center. And for this, we're going to use I omega. So I naught omega naught is going to be I final omega final. And we're solving for omega final. Now the I's. Well, you have two things. You have the merry-go-round and you have the person. The person is behaving like a point mass going in a circle. Okay. So I'm going to add up the merry-go-round's moment of inertia plus the person. Okay. So for the merry-go-round, it's a disk. So it's 1/2 big M R squared. And then for a point mass, the moment of inertia is simply M R squared. I'm using little m there because it's me. And then times omega naught, which I'll throw in there next line down. Afterward, you still have the same merry-go-round, so the moment of inertia of that doesn't change. Now at this point, your radius, when you get to the center, your radius is basically 0. So for all intents and purposes, the moment of inertia of you is 0. And then that's going to be our omega final, okay? So now we're going to plug our numbers in. We got 1/2 times 200 times the radius. Oh, I didn't give you the radius. Sorry about that. The radius, we're going to say the radius here is 2 meters, okay? Which would be a pretty big merry-go-round, by the way. So 2 squared plus my mass, which is 80 times 2 squared. Omega naught was pi over 2, okay? And then over here we have 1/2 times 200 times 2 squared plus 0 and omega final. And if you work all this out, all this ends up being 720 times pi over 2. This all works out to be an even 400 times omega final. And if you solve that for omega final, in terms of pi, I get 9/10 of pi, okay? Okay, or if you wanted to write that out in a decimal, I get about 2.83 radians per second. Okay, so But for the next part of this, I'm going to leave it in the pi thing. So again, that's 2.83. All right, so that's your final angular velocity. Now notice it was half pi, now it's 9/10 pi, so it's almost double, okay? And try that out, by the way. If you ever get a chance of any kind of merry-go-round or anything that spins like this, walk from this outside toward the inside while it's spinning, and you will notice it speed up. And by the way, the more people that do it at the same time, the greater the effect. So if you and 4 or 5 of your friends are on the outside of the merry-go-round, and you all crawl toward the center at the same time, wow, does it really speed up. It's nuts. Okay, so try it out sometime. All right, now the other part I asked you about was work. Okay, so how are we going to calculate work? All right, well, one way would be to try to calculate the centripetal force, or well, in this case, it's friction, but it's the force pushing you in would be friction, which would be equal to mv squared over r. And then you could try to integrate that force, because you know that force ain't constant. And you could try to integrate that from r to 0. And you could do that. It's really complicated, though, and takes a lot of calculus. However, there's a very easy way to calculate the work done. We know the net work, which is what I'm trying to find, is simply your change in kinetic energy, which is your kinetic energy final minus your kinetic energy beginning. So our net work is, now this is rotational kinetic energy, it's 1/2 I omega squared. So my final was 1/2. The I already figured out. The final I up here, we got 400, so I'm just going to use that. And omega final was 9 pi over 10, and I had to make sure I squared that final omega, minus 1/2 my starting moment of inertia was 720, that's right there, and then the initial omega was pi over 2, and I got to make sure I square that. And I plugged my numbers in the calculator. I got 1599 minus 888, and I got 711 joules. So that's how much work it took for you to pull yourself from the rim of the merry-go-round toward the center. Okay, so that's my one mathematical example I'm going to do on this. I did promise you one conceptual question, and this will actually lead into the last video that you're going to watch for this unit. So here's the conceptual question, and I have actually seen these kind of questions on an AP exam. So first question, a cart collides and sticks to another cart. When the collision occurs, what is conserved? Okay, so hopefully you guys can all look at that and give the correct answer. And the correct answer is linear momentum. Okay, the total force, if I look at this, when cart A hits cart B, there's a force, and that's an equal and opposite force on cart A. Okay, and if I look at the two-cart system, the total momentum of that system is conserved. That force on that system is 0. Okay, so there you go. Kinetic energy is lost, by the way. This is an inelastic collision. So, and it turns out in this collision, I believe you would lose exactly half of your kinetic energy. So B cannot be correct. Therefore, C cannot be correct. And since A is correct, D cannot be correct. So that would be like a physics 1 or a beginning physics question. Now here is the physics C question. Are you guys ready? A ball of putty strikes and sticks to a rod hanging from a pin like this. What, if any, of these things are conserved? Okay. So, and now I've got, of course, more answer choices, making it a little more exciting for you too. Okay. So the putty sticks to the rod, and the rod and the putty swing off together. At the moment of collision, what is conserved? Okay. Well, I can start with what's not conserved. Definitely not kinetic energy. It's still an inelastic collision, so you're going to lose a lot of energy here. Therefore, it cannot be D, and therefore it cannot be F, okay? And therefore it cannot be A, B, and C above. So we've eliminated half the answers already, okay? Now, let's see. It could be A, B, or E. I'm going to tell you right now it's not none. Okay, so it could be A, B, or E, but which one is it? Well, let's start with when the collision happens. So here's the moment of the collision. Here's the pin, and here's the ball sticking to the rod, okay? If you try this out, and let's say you hold the rod when you do this, when that putty hits that rod, your hand is going to have to push left to keep that part of the rod still, to keep the pin still. That is an external force to the rod putty system. So since there is an external force to the rod putty system, linear momentum is not conserved, and therefore E can't be right either. It turns out your correct answer is B. Now, let me draw the FBD of this. So this would be like the force of the pin on the rod. At the same time, the putty hits the rod and the rod hits the putty. Now, those two forces are equal and opposite. Newton's third law. You'd also have the weight of the rod and the weight of the putty. In order for angular momentum to be conserved, net torque about some axis has to be zero. Is there an axis about which the net torque is indeed zero? Well, yes, there is. The pin. All these forces, these two here cancel. The putty hitting the rod and the rod hitting the putty, they cancel. So the net force of those two on the system is zero. The weight of the putty, the weight of the rod, and the pin force all act through this axis. So none of them cause torque about that axis. So the angular momentum about the pin, and only about the pin, is conserved. Okay, so that's going to lead you to the next video, which you're going to watch on how to actually calculate that. All right, so I hope that video was helpful, and thank you very much.